We stand today on the brink of a revolution in cryptography. Yeah, those words, those famous words, led to what is known as RSA today, the public key cryptographic algorithm. But how did those words lead to what we call RSA? What is RSA? How does RSA work? And why is it important? What am I even making this video for? Sit down. I need to tell you a story, but before we understand what RSA is, we need to understand how it came to be. So let's go back to 1970s, I should say. We'll start with Whitfield Diffie. Diffie, as he's known as. See, Diffie was, well, he wasn't a computer guy. He didn't know computers that well, but he was very interested in network security. You see, before 1976, there was a fundamental issue with computer security or network security, and it's not the issues that we have today. The issue was with cryptography. You see, at the time when we were using cryptography, there was only one key to encrypt and decrypt data. That means in order to send an encrypted message, a user, you need to encrypt a message with the key, but send that key to the recipient ahead of time over an insecure channel at times. So you need to give your key to someone else, and then you can send your message, your encrypted message. That person can use that same key to decrypt your message, re-encrypt a new message, and send it on back to you. It seemed to work, but there were two fundamental issues. You see, the first issue is if someone gain access to that key, they can now encrypt and decrypt data. Meaning they can change your data, they can send it on its way, they can read the data if they intercept it. There's a lot of issues that happens with that. The second fundamental issue is the issue of authenticity. You see, if user C were to come in and intercept that message, decrypts it, changes it, re-encrypts it, and sends it on its way, there's no way to verify that the data was actually changed in any way. And there's no way to verify that the recipient who you sent the information to didn't just send the message as it was. That was the second fundamental issue. Digital signatures did not exist, and the PKI infrastructure didn't exist as well. So what did Diffie do? You see, Diffie couldn't figure this out. At least not yet, around 1970s. He worked on it, and at times he was funded under the table, right, from NSA through some kind of money laundering way. You see, NSA would fund the Navy, who would then fund Diffie, and Diffie would continuously work on this network security issue, which was cryptographic related at the time. Diffie eventually hit a point where he was stumped a bit, and in order to overcome this, he flew out to the IBM Watson Research Lab out in New York to meet one of the very famous cryptographers, Horst Feistel. Yeah, the Feistel that created block ciphers for encryption. We'll get into that maybe in another video. But he was important, he was smart, he was well known in the cryptography community, and Diffie wanted to speak to him. But when Diffie arrived to the IBM Watson Research Lab, Feistel was gone. Well, he wasn't gone for good, but he had left for the weekend. You see, Feistel loved to vacation in Cape Cod, and that's what he did. He was out. Well, then what did Diffie do? Diffie reached out to Feistel's boss, a man named Alan Conheim. You see, Alan was very secretive about this whole network security issue. At the time, NSA believed that an encryption algorithm should remain secret, as well as the encryption key. Well, the key made sense. The algorithm, still up for debate, and Conheim kept the secrecy, though it wasn't out of the ordinary that he remained secret, but he did leave Diffie with one piece of advice that would change the cryptographic world today. You see, Conheim told Diffie, two people can work on a problem better than one. Then he goes on to say, he can't tell you anything about this stuff, meaning he can't tell Diffie much of the things about this stuff, but he has a good friend that can probably help. In fact, his good friend's name was Marty Hellman, and Marty was very much interested in solving the issue with network security in the 1970s, just as much as Diffie was. Well, later, Conheim regretted giving this piece of information to Diffie, but it still helped shape the world today. Diffie took that information, flew back to California, where he lived with his wife, gave Marty a call, had about a 30-minute conversation that eventually escalated to a dinner with Marty. They hit it off, became really good friends, great researchers, and partners together. It was Whitfield Diffie and Marty Hellman against the network security issue. And in 1976, a new article was published by the two, called New Directions in Cryptography. They did it. They identified the two issues, the issue with using a single key over an insecure channel, that key distribution issue, and the issue with authenticity, the digital signature issue. You see, Diffie and Hellman proposed a new idea, a public key infrastructure based idea. Now, the idea itself wasn't necessarily new, but it was more detailed and outlined in this article. And the idea proposed to use two keys instead of one. One key, we'll call that our public key. When we're encrypting information, the public key will be responsible for encrypting. Doesn't matter if that key gets stolen or shared, because it can only encrypt and cannot decrypt. And we have the corresponding private key that can only decrypt. That key should never be shared, and that key should never be stolen, because then you lose the integrity of that data. So how did this work? Well, let's go back. You want to send a message to your friend again. This time, you ask your friend, hey, can I have your public key? Your friend gives you their public key. Now, it doesn't matter if an attacker steals that key. It's only used to encrypt. You take your friend's public key, you encrypt the data, you go ahead and send that encrypted data to your friend. Now, the only person in the world who can decrypt the data is your friend, because they hold their own private key. Yep, this was a way to send data using a key that only encrypts to the very person who gave you that key, and also the very person who holds the only key in the world that can decrypt that information. So once your friend gets the information, they decrypt it, and boom, they get the message. Reverse the process. Your friend asks you for your public key. You give your friend your public key. They encrypt the data with your public key, sends it back to you, and you can decrypt it with your own private key. It was the PKI infrastructure, and it solved the issue with network security. But what about that issue with digital signatures? What if someone did steal your friend's private key and change the data? Well, what happens? Well, almost inverting that process solved the challenge of digital signatures. Let's take the example again. You send data to your friend. This time, you take your private key and the data, you hash the data, meaning you send it through a one-way function that's not reversible. You take that hash and you encrypt it with your private key. Now, you share your public key with your friend and you send that hash along its way, the encrypted hash. Your friend receives that information and you reverse things, right? So you encrypt with your private key this time. You can decrypt with your public key. Now, anyone can decrypt this hash. It's just a hash. It's not information that is meaningful. But the secret is in how it works. You see, every time you change a piece of data, the hash changes. Meaning, if your friend gets the encrypted hash and decrypts it with your public key, if the hashes match, that proves the data wasn't changed. But if the hashes don't match, well, that means the data was changed in transit. You can identify that someone might have altered that data. Oh, it was a fail-proof system, at least before hash-based attacks aroused, matching hashes, birthday attacks, things like that. At the time, it was a foolproof system. You can send a message that can't be decrypted by anyone but the receiver, and you can send an integrity check to that receiver so that they can verify the data wasn't changed at all in any of the steps in that communication flow. They did it. Whitfield Diffie and Marty Hellman, they solved the issue with the network security one key encryption with this two key based infrastructure. But how do you apply that to computers today? You see, the article wasn't enough. It was a cool concept, but no one knew how to apply that to computers. In fact, it was actually pretty challenging to apply that to computers. Enter RSA, Rivest-Shamir-Adleman. The three individuals that created RSA inspired by this PKI article that was created by Diffie and Hellman. You see, Ron Rivest, Adi Shamir, and Leonard Adleman publicly, we'll say, disclosed a new type of public key encryption algorithm. Well, this was in 1977. This encryption relied on two prime factors and used that as part of the public key. So the encryption component of the public key infrastructure. And the success of this algorithm relied on the difficulty that arises with the two prime factor problems. Meaning, it might be easy to multiply two prime numbers together into a larger prime number, but it is relatively difficult to factor a large number into two smaller prime numbers. That was the whole secret of RSA, and it worked really well. In order to help you understand how that whole flow worked, let's take a look at the public key digital signature architecture, and then we're going to look at RSA. We'll get into RSA and we'll break down how it works at an overview and at a detailed level. You'll be experts by the time this video is over. Check this out. Okay, so this is a basic PKI infrastructure. Pretty much the same PKI infrastructure that RSA was built upon. One thing to point out about this specific diagram is that the communication flow only goes one way. I did that on purpose for simplicity's sake, but in a real PKI system, communication is a two-way thing. So it's almost like a mirror, right? So Bob has to communicate with Alice, but then Alice has to communicate back with Bob. And the process in which Alice communicates back to Bob is pretty much a mirror in the way that Bob communicates back to Alice, just with different keys. I'll show you what I mean. So if you look at the very top, that's a little of what I mean. You have Bob's public key and Alice's public key. So what happens is Bob generates a public key and a private key, and then Alice does the same thing. She generates a public key and a private key. Now, Bob needs to be able to encrypt messages to send to Alice so Alice can decrypt. Now, with Bob's public key, the only thing that can decrypt the message is Bob's private key. So would it make sense for Bob to encrypt the message with his own public key because he's the only one who can decrypt? So what he does is he sends the public key over to Alice. So now Alice owns Bob's public key, and Alice does the same thing. She sends her public key over to Bob. Now Bob owns Alice's public key. Now Bob can encrypt the message with Alice's public key, and Alice can encrypt the message with Bob's public key, and Bob can decrypt the message for him. Alice can decrypt the message for her. Okay, in this flow, let's look at what happens when Bob sends a message to Alice, an encrypted message. First, we have Bob that drafts the message. In this case, the message is "Hello Alice," following this purple ball looking thing over here. Once Bob generates that message, he takes Alice's public key, the one that Alice gave him, uses that public key to encrypt the message. In this case, we'll say RSA encryption. Okay, great. The message is encrypted. Now, Bob sends that message over to Alice. Alice receives that message. We'll say her computer receives the message, right? At this point, Alice has a message but can't read it because it's encrypted. So it's just a bunch of letters right now. But Alice knows that this message was encrypted with her own public key. So she takes her private key and decrypts the message. And the ending result of that message ends up being "Hello Alice." Alice did it. Bob did it. Bob sent the message to Alice encrypted. Alice was able to use her private key to decrypt it. And now Alice is ready to send the message back to Bob, which we just reverse the process. Alice encrypts it with Bob's public key. Bob gets the message and decrypts it with his private key. Okay, that's all good, but we're still missing a piece. Bob still needs to digitally sign a message so that Alice can verify the authenticity and integrity of that message. So Bob does just the opposite here. Now, Bob will take that same message. Before Bob encrypts that message with Alice's public key, he takes a hash of that file, that message file. Then what he does is he takes his private key and he encrypts the hash with his own private key. Now, when you decrypt that encrypted message, you'll just have a hash. That's all. Okay. Now Bob sends that encrypted message, right, which is just a hash at this point, over to Alice's computer. Alice already has Bob's public key. So you see what Bob did there? He actually reversed it. He didn't use the public key to encrypt. He used his private key to encrypt, meaning that Alice has Bob's public key and she can decrypt this encrypted message that is really just a hash at this point. So what Alice does is she uses Bob's public key to decrypt that message and grab the hash. Now, Alice has a hash of the message that she is supposed to be receiving. So when Bob goes and sends her the encrypted message, she receives that message and she already has a hash that she decrypted. She takes a hash of the message and she takes the hash that she used to decrypt this message with and she compares them. And if the hashes match, that tells Alice that the file has been unchanged. But if the hashes are different, that means that at some point that file was changed, whether in transit or before it left to go into transit. So Alice will only decrypt the message and read the text if the hashes match. That's the whole digital signature piece, the authenticity. That's pretty much how the PKI system works. Now, of course, when Alice sends a message, this whole process is reversed. Alice now has to hash the message and encrypt it with her own private key. Bob has her public key. So when she sends it over, Bob can decrypt it with her public key and he has a hash. And then when the actual encrypted message comes, he decrypts that message. He can compare the hashes and verify that the message is unchanged when it goes back to Bob. So this is how the infrastructure is. It's not too complicated if you're kind of breaking things down and looking at it, but it is important to know because this is how RSA kind of works. This is what RSA was built on. Now that we know the architecture, let's look at an actual example of RSA by hand. Let's jump in. Okay. So we know that RSA uses prime numbers, but we need to actually understand how it works at the mathematical level. In order to understand that, we're going to do it by hand. We're going to do the complete encryption by hand, math only, and complete decryption. So we'll take the Bob and Alice scenario and we'll run through that. So when we're encrypting a message with RSA, we need to set up our encryption formula. And to do that, we need to first start with the two prime numbers that are very commonly mentioned in RSA. We'll call that P and Q. So we'll say P and we'll say Q, where P is equal to a random prime number and also Q. So we'll say P is 11 because 11 is prime. It has no factors, right? Q is 17. Again, Q is prime. It has no factors. So when we talk about our prime factors, now we have P and Q. The next thing we need to do is set up what is called the RSA module. And that's represented by N. So N is our module. This is actually, it's called module, but when you run the encryption and decryption formula, you actually have to take the modulo N. That's part of the RSA algorithm for both encryption and decryption. So in order to calculate N, it is actually just a multiple of P and Q. I wrote that backwards, but you get the point. Multiple P and Q. So if we're going to do our N, right, N is the multiple of 11 times 17, which means that N is 187. Boom. Let's move that over. Boom, 187. So now we have our N. We can move on to the next step of the RSA process, which is basically calculating our public and private keys. So public and private key pairs, public to encrypt, private key to decrypt. So to calculate this, we have our public key. We'll call that pub. This is actually equal to N. So that 187 comma E. E is just a variable placeholder for now. It just stands for encrypt. So we just add that placeholder. So we know it's 187 comma placeholder for E. Private key, you can probably guess already, that is N comma placeholder for decrypt. So that's our private key to decrypt the message or the ciphertext that will become the message. Okay, we have our public private key, we have N, but we don't have E and we don't have D yet. So we need to figure out how to calculate E and D. Fortunately for RSA, we actually can choose E based on a specific rule. But before we get to that rule, we need to calculate phi, which is the Euler phi function of N. We need to calculate that first. So that's represented by a symbol here, right? And then the function N. And phi is actually pretty much just P minus 1 times Q minus 1. So that's the formula to calculate phi of it, right? So P minus 1 would be 11 minus 1 and then multiplied by 17 minus 1. Relatively easy. We can calculate that. 11 minus 1 is 10. 17 minus 1 is 16. And we know that this is equal to 160. So we found our phi N. Well, in this case, this would be phi of N equals 160. By the way, N is 187. So phi of 187 is equal to 160. Just keep that in mind. Okay, we have phi. Now we're ready for our rule on E. Oops, there we go. E has to be equal to a number that is co-prime of phi. That means this number can't share the same factors of phi, right? So we know that phi of N, oops, and I meant to put 160 there, not 16. Boom. So E has to be co-prime to 160. That's it. So we need to pick a number that doesn't share the factors. That's it. We could pick 17. Oh, sorry, there is one more rule of E. E also cannot share, when I say factors, it's not really factors. E cannot share the same divisor as phi. That's what it really is, not necessarily factors. So any number that is divisible by phi cannot be divisible by E and vice versa. So if E were to be 4 and phi were to be 160, they're both divisible by 2. So that wouldn't work. In this case, E is divisible by, and it can only be divisible by 1. That is the rules there. Promise that's the last rule. So in this case, 17 is divisible by 1. So that fits, can be divisible by 1. And it can't share other divisors. So there is no other divisor that 17 has. So 17 actually works by default. And 160 is not divisible by 17. So E being 17 actually works. So we have our encryption. We have N, which is 187, comma, 17 for E. I'm just gonna jot E down as 17. Boom. Let's erase this. Now that we have E, we can calculate D. D is a very strange formula because D is pretty much a multiplicative inverse of E. So basically what that means is that D times E, right, mod phi should equal 1, that inverse there. So we have our formula for the decryption formula, and that would be D times E mod, and then phi is, I'm just gonna write the number of phi. 60 has to equal 1. So we know that E is 17. So D times 17 mod 160 has to equal 1. So modulo, what that is basically the remainder of something. So think in terms of long division, right? If you have, 161 divided by 10, right? If you did that in long division, you'll probably end up with 16 remainder of 1. And that's what that remainder right there, that would what would be called a modulo. So the modulo is just a remainder. You want to think about it that way. So in this case, we're saying d times 17, right? Modulo of 160, meaning divided by a 160 has to have a remainder of 1. So that's an easy way to kind of interpret this. So in this case, we need to find a number that is a multiple of 160. Well, to make this equation a lot easier, what we can do here is subtract 1 from both sides. So now d should be d times 17, right? Minus 1 mod 160, terrible 160, but that's all right, equals 0. And if the modulo is 0, that means the remainder is 0, which means the numbers should evenly divide with each other, right? It should be an equal match. So we can say d times 17 minus 1 divided by 160 works. It has to be a multiple of 160. I did do some math, and d is 113, right? 113 times 17 is equal to 1921. And if you minus 1 from that, you get 1920. And 1920 does evenly divide by 160 and have a remainder of 0. D can be 113, and that would work. D could also be a higher number, but generally with RSA, you want to choose the first number that matches with D. So your decryption variable is 113, meaning that the private key is 187, 113. So keep that in mind. All right, let's erase this. Okay, we are finally ready to encrypt our message, except we don't actually have the message yet, but we're ready to encrypt it. So let's actually go through the encryption formula. So to encrypt the message, we need to come up with the output. The output is a ciphertext C. That's just an encrypted message. C is equal to the actual message in plain text to the power of our encryption variable, and that's going to be modded with, or modulo, right, with n. So we have our public key here, right? We have n, comma, e. We have our public key in the formula, and we have m, our message, and together that the right side of the equation should equal our ciphertext, which is the encrypted message. Now we just plug in the variables. We actually don't have m yet, so in this case we're going to simulate m, right? Let's say we want to send the word hi to Alice. We're Bob, by the way. We're trying to send hi to Alice. With RSA, what generally happens is this string will be encoded into a number. I don't know, we'll say 88. So now, let me fix that. There you go. So now our message is 88 because we encoded it. And then when Alice decrypts it, she's going to also decode it. So let's plug these numbers in. C is equal to 88 to the power of E. E is 17 mod N, which is 187. Okay, now if you run this into a calculator, 88 to the power of 17, you're going to get a really big number. So I'm not even going to convince you to do that. There are ways to actually break it down to be a lot easier, right? You can break this down to 88 to the power of 10 and then 88 to the power of 7 and then multiply the two together. But we won't do that. We're going to do the easy way and just kind of run that through a power calculator. And 1 second while I actually do that. Okay, running through a power calculator, we get the ciphertext equal to 121, which means we can now send our message to Alice. So Alice has 121. Nice. Alice has the ciphertext, but now she needs to decode it back to the plain text message. Let's figure out how she needs to do that. First, we're going to erase this. Okay, Alice needs to decrypt. Decryption formula is pretty much the same as the encrypt. It's just reversing the variables, and then you're plugging in your private key instead of your public key. So decrypt will be reversed. So instead of finding the cipher, you're going to find the message, and that is going to be equal to the cipher raised to the power of your decryption variable mod the other part of your decryption key, which is n. So when we plug this in, we actually don't know the message because we're Alice now. But we do know the ciphertext, which is 121. 121 raised to the D, and we do know what D is because we calculated that. It's 113, which would mean the 121 to the power of 113 would be a really large number. Split it up, 10, 10, 10, 10, 10, 10, 10, 3. You know, you could do that kind of math. And then mod N, which is 187. Now run this through our power calculator, and we get M is equal to 88, which we technically already knew that, but we still needed to run it through our power calculator to make sure our decryption formula is working correctly. So Alice now has the the encoded message, and then Alice needs to run this through the decoder, right? The other part of RSA, and that decodes to hi. So Alice got our message. We decoded the message to hi, and we did it by hand. We didn't need computer power. So with RSA, just know that when you're running this through a computer algorithm, the key sizes are not as simple as 187, 17 for your encrypt. It is much larger numbers, significantly larger numbers. So doing it by hand is not feasible. I mean, you probably can. It's going to take a really long time. Computers are a lot better at handling those extremely large numbers, and that's why it works so well. Just know also, when we're talking in terms of the private key, as you can probably guess, that formula for private key, right? D times E mod V, right? That formula, it would be significantly harder to find D, which is your private key, if the numbers were significantly larger. So that's where the secret in RSA lies, the complexity of the modulo function in conjunction with your factors, your prime factors there. That said, there are ways, at least upcoming ways, to kind of defeat the RSA algorithm, but you just learned how to encrypt and decrypt by hand with RSA. Cool. We just learned RSA. We just mastered RSA. But our story doesn't end here. You know that, right? Did you really think Diffie and Hellman would stop at an article? Who is this guy? The story continues. In fact, Diffie and Hellman go on to meet someone named Merkle, and together, the three of them work hard at a new type of PKI algorithm, a new asymmetric or public key based algorithm called Diffie-Hellman. Same Diffie-Hellman that's used in TLS 1.3, IPsec tunnels, and many more standards. I believe it's also used in like SSH protocol. Don't quote me on that SSH one. But we need to learn about Diffie-Hellman, and then we can learn about how to break it. What's the fun in learning about how something works if we don't know how to break it? Yes, there is something called superpositioning when it comes to quantum-based processors, and that allows quantum processors to perform multiple calculations at the same time. That means multiple guesses at the same time. Now, of course, guessing is not really going to help anyone. We just randomly start guessing numbers. The chances of you getting the right number is still slim if the number is really high. But we can use something called Shor's algorithm to make sure that every time we guess, we get closer to the answer, and our chances of getting the right answer increases. It's a weird concept, right? But we'll learn that in another video. So stay tuned. Make sure you're hitting that notification bell. Make sure you're commenting for the algorithm and subscribing and liking the video, because when those other videos come, you know, with Shor's algorithm, don't say I didn't warn you. Also, just remember, we're ethical here, okay? So when quantum-based processors are commercialized, I don't want to see you guys going out there and trying to crack these latest encryption algorithms and things like that, using these Shor's and Grover's algorithms and all the other type of old math problems that have resurfaced in the modern age. None of that. Thanks for watching the video. I appreciate you guys. Pat bow.